I heard about the digital capabilities of this facility, but I had no idea it was so centralized.
Yeah, it's pretty amazing how much information you can get from a display screen. Let's have a seat and I'll show you.
Okay.
Digital control systems provide versatile and efficient process control and data acquisition in many industries. Terminology and symbols used to represent control systems have been expanded to include digital technology. Standards have been developed to provide universally accepted symbols that represent digital as well as analog control systems. ISA's Standard 5.1 contains definitions of process terms associated with digital technology. The symbols and designations used to illustrate control systems are shown along with sample diagrams that serve as examples of how they are used. It's important to remember that the application of symbols and identifications is often modified to meet the needs of specific industries. So be aware of the practices within your industry, the manufacturer's definitions, and your plant's preferences. The symbols and identifiers used in digital systems are based on those used in analog systems. To help us understand the functions represented by these symbols, let's review the characteristics of digital control systems. One of the most visible aspects of most digital control systems is a shared video display. Processes include many variables which must be monitored and controlled. With digital systems, these variables can be checked at a remote location using a shared display. A shared display is a device that allows interface with the process to provide and display measurement and control information from a number of different locations within the process. With a shared display, often an entire process can be monitored on one screen. A shared or multifunction controller can control several process variables simultaneously. This type of controller contains pre-programmed algorithms or sequences as part of the control function. These algorithms make the control functions accessible, configurable, and assignable. Let's see what these terms mean. Functions that can be used or seen to control process functions are called accessible. For instance, a set point change can be made to a process variable. Configurable means that the control functions can be selected or rearranged through the software configuration program or some method other than rewiring. Assignable refers to a feature that permits a signal to be directed from one device to another without the need for switching, patching, or changes in wiring. Processes must be constantly monitored and controlled. Since a multifunction controller often must control several process variables simultaneously, it can scan or sample each of a number of variables. For instance, the controller might sample flow rate, then temperature, and then level, continuously repeating the sequence to monitor and control the process. Usually, as each variable is sampled, the state or value of the variable is determined. So scanning is often related to other functions. For instance, it might be combined with recording, because while scanning, it can also log a current record of the value or states of all the variables in a process. Your workbook describes the characteristics and components of digital control systems in more detail.
The throttle pressure on this video display.
Yeah, and you can also control the airflow and the oxygen from this display.
These video displays are great.
You may already be familiar with many of the symbols used in instrumentation diagrams. Understanding these symbols helps to interpret these diagrams for troubleshooting or diagnostics. A plain circle or balloon indicates a discrete instrument. A circle in a square represents shared display or shared control functions. A diamond in a square represents a programmable logic control or PLC. A hexagon indicates a computer function. Function blocks designate the computations and conversions within a loop or instrument. You'll see function blocks used in several ways. As a standalone symbol that represents only the functional aspects of a loop. As a flag designating a function of a specific component. Or on a signal line adjacent to a shared controller. Let's look at some of the types of function symbols that you may find on a diagram. This is the symbol for the summing function. This function indicates that the output will equal the algebraic sum of the inputs. Another function symbol frequently seen on instrumentation diagrams represents square root extraction. A square root function symbol, like the one we see here, indicates that the output signal is the square root of the input signal. As you know, the letters in the top part of the balloon are the functional identifiers. The first letter identifies the measured or initiating variable. The succeeding letters represent a readout or passive function, followed by the output function. So the functional identifier here tells us that this is a level indicating control. If Y is the first letter, it represents controls that are event-driven, such as on this valve. Y might also signify a state or presence. As the output function, Y indicates compute or convert, such as this square root extractor. Typically, the letter A, used as the first letter, identifies most analysis functions. The variable being analyzed is usually identified by a note outside the balloon. If A is the second letter, it usually indicates alarm. A table of identification letters in ISA Standard 5.1 is included in your workbook. The presence or absence of lines within the symbol gives you information about the location of the device. A single line through the center indicates that the controller is in a primary location, usually the central control room, and is accessible to the operator. A broken line indicates a location behind the panel that is usually not accessible to the operator. No line indicates that the device is field-mounted. A double line indicates an auxiliary location. Now, let's look at lines that represent connections between devices. You may already recognize this dashed line as the symbol used to represent an electric signal. But the international symbol, a solid line with triple crosshatches, is also used to indicate an electric signal. This line symbol represents an internal system link that may be a software or data link between components. Notice there is an arrowhead at the end of the internal system link. Arrowheads show the direction in which the data is sent. This information is important when troubleshooting communication paths. Electromagnetic or sonic signals are represented by a guided or not guided line symbol. A signal that is guided, such as a fiber optic signal, may be represented by this symbol. A sonic symbol is an example of a signal that is not guided. These symbols indicate an electrical binary signal. Backslashes are added to the standard line symbol to indicate that this is a binary signal. Now, let's look at another line symbol. During the early stages of system design, before the hardware and software have been specified, this symbol is used to indicate an undefined signal. Although the type of signal lines have not yet been identified, an undefined signal line shows the communication paths between the components. As you can see, line symbols let you know the direction and types of signals that connect the components in a system. Being able to interpret them helps you understand how an instrument system communicates and can provide valuable information for troubleshooting. You'll also see other symbols on the P&ID, such as those for the primary element and final control element. The primary element, or sensor, is the part of the loop or instrument that first senses the value of a process variable to determine an output signal. The final control element directly controls the value of the variable of a control loop. Usually, the final control element is a control valve. Your workbook contains additional information about primary element and final control elements and the other symbols discussed in this segment.
These displays are great.
But if you really want to troubleshoot in the loop, you really need to look at the P&ID.
There are several types of diagrams, and each has a different purpose and different degree of detail. Simplified diagrams show the points of measurement and control. Conceptual diagrams emphasize control functions. Detailed diagrams describe the specific hardware and signals in the control system. Let's look more closely at each type of diagram and see what information it provides. Simplified diagrams are usually created during the early stages of system design, before the specific hardware and types of signals have been selected. A simplified diagram is used to orient you to the process operation. This example illustrates a distillation column control system. The balloons have abbreviated identification and show the points of measurement and control. The path and direction of process flow is indicated. The signal lines are undefined. Let's look at a section to see what we can learn about a process system from a simplified diagram. This balloon, designated F, is connected to the process line that enters the column. From this, you know that the flow of the process fluid is measured at some point before it enters the column. This line is product feed and is connected to the center of the column. You can also see that hot oil enters and exits a heat exchanger called a reboiler. The balloon connected to the supply line to the reboiler is identified FC and indicates that flow is controlled at this point. An undefined signal line connects the flow controller to a valve. Therefore, the flow of hot oil is measured and controlled as it enters the reboiler. The process lines indicate that process fluid exits the column, passes through the reboiler, and returns to the column. You know that a controlled flow of hot oil passes through the reboiler to increase the temperature of the fluid in the column. This balloon, labeled LC, indicates level control connected at the lower portion of the column and linked by an undefined signal line to a valve in the process line. This indicates that the level of the process fluid in the column is measured and maintained by controlling the rate of fluid flow exiting the column. This balloon, labeled A, indicates that the process fluid is analyzed as it exits the column. So from a simplified diagram, you can determine the basic operation of the system by identifying the points of measurement and control and the direction of the process flow. This is a conceptual diagram of the same distillation column system as on the simplified diagram. You can see that there are a lot more symbols associated with controlling the process. The hardware and signal lines are still as yet undefined, but the diagram now includes some function symbols. These symbols indicate some of the functions of the process control instrumentation. So, a conceptual diagram focuses on the functions that control the process. As you can see from the function symbols, there are a number of process control and calculation functions. Simple balloons with abbreviated symbols identify the variables. Undefined signal lines are used to identify the signal paths. To see what information is indicated about the control of the system, let's interpret the same section as on the simplified diagram. This is the hot oil line to the reboiler. This balloon indicates that flow is measured at this point. A signal representing the measured value is sent along an undefined signal line to a square root function. The square root is extracted, and the signal continues to a multiplier function. The linearized signal is then multiplied. But by what is it multiplied? When you trace the signal line, you see that there is a second input to the multiplying function from a differential temperature transmitter. So the linearized flow signal is multiplied by the signal representing the differential temperature. A note adjacent to the function block shows the algorithm performed by the multiplier function. After the value of the flow rate and the differential temperature are multiplied, a signal representing their product is sent to a flow controller. The flow controller also has a second input. Tracing the signal line, you see another multiplier. It also has two signal inputs. The first input is from a flow transmitter connected to the feed line to the column. The transmitter senses the flow rate through the process line and outputs a corresponding signal. The square root is extracted from this signal, and the linearized signal goes to a time function block. Here, the output signal will equal the input flow value averaged over a period of time. The signal then goes to the multiplier function. The other input to the multiplier function originates here. The letters in the balloon indicate that this is an analysis transmitter. The analysis transmitter is connected to the process line, which carries fluid from the column. So its output signal represents analysis of process fluid from the column. This signal is sent to an analysis controller and on to the multiplier function. The multiplier then sends an output signal based on the column feed rate and the bottom's product analysis to the flow controller. The flow controller receives input signals based on the values of these two multiplier functions to operate a valve that controls the rate of hot oil flow in the system. There is also an analysis of the overhead product. This analysis, along with the forward flow of the overhead from the accumulator, is also part of the temperature control calculation. So the rate of hot oil flow is determined by several variables and functions. Looking at the functional aspects of a system can be a valuable tool to understanding how it operates. Once the hardware has been selected, specific instrumentation symbols on a diagram illustrate the control system. Let's look at another example. This detailed diagram shows the same section of the distillation column control system as shown on the simplified and conceptual diagrams. Notice that the diagram includes specific symbols for equipment and functions, as well as specific signal lines and system links. This detailed diagram will show how the different instruments work together to control the flow in the hot oil supply line to the heat exchanger. As hot oil flows through the supply line, it passes through this orifice. Connected to the orifice is an instrument balloon representing a flow transmitter. This is a discrete field-mounted instrument located in loop 900. The flow transmitter sends an electrical output signal to the square root extractor, also in loop 900. The letter A after the loop number indicates that there is more than one computing function in this loop. The symbol indicates this is a software function in a shared controller that is not accessible to the operator. The letter Y in the functional identifier indicates that this is a computation function. The function flag attached indicates that the computing function is square root extraction. The output from this function is a data link to a second flow computing function, FY900B. This function is also not accessible to the operator. The function designation flag identifies this as a multiplier function. The second input for this multiplier function is an electrical signal from a discrete field-mounted differential temperature transmitter in loop 920. This transmitter has two electrical inputs from the temperature sensors. This note identifies RTDs as the temperature sensors, so RTDs provide the input to the differential temperature transmitter. So the differential temperature transmitter sends a signal to computing function 900B. As we said, this is a multiplier function, and the product of its inputs is sent by this data link to the set point on FIC 900. This is a flow indicating controller in loop 900. From its symbol, you can see that it is part of a shared display, shared control. The center line indicates there is operator interface at a primary location. The note adjacent to the symbol identifies this as a flow rate alarm that actuates at high and low conditions. That means that the alarm is activated whenever the flow rate of hot oil to the reboiler is outside those limits. This flow indicating controller has a second input from flow multiplier function 901C. Multiplier function 901C also has input signals from two sources. One input originates at a field-mounted analysis sensor in loop 941. This sensor sends an electrical signal to an analysis transmitter. This device is also field-mounted. The analysis transmitter sends an electrical signal from the field to the control room. You know this because the symbol for the analysis controller indicates that it has a shared display, shared control function that is accessible. This note indicates that the analysis controller has an alarm that activates when it reaches a high limit. The signal from the analysis controller is received by multiplier function 901C. The other input to this multiplier function is generated by flow computing function 901B. This is a time-oriented function that is part of a shared control unit and not accessible to the operator. This note indicates the source of the flow signal to FY901C. Multiplier function 901C multiplies the inputs from FY901B and AIC 941 and transmits the information via a data link to the flow indicating controller in loop 900. The controller sends an electrical signal based on its two inputs to a final control element, in this case, a control valve. The final control element is an electrically actuated two-way control valve, configured to fail closed in case of signal or power failure. You can see that the detailed diagrams show how discrete and shared display shared control instruments are used to control a process. Each of the instrumentation diagrams provide a different level of information about the process system and how it functions. You may need to consult more than one type of diagram to fully understand a system's operation. And remember also that you can learn other information about the system from the information blocks at the bottom of the P&ID. So always look at your P&ID before beginning any work on the process system, and be sure to follow your facilities and manufacturer's safety procedures. Your workbook contains more information about process and instrumentation diagrams and the other information covered in this program.